All right. Hello, everyone. As Maya introduced me, I'm Sasha Levina. I'm a graduate student at UC San Diego, and yes, I will be talking about the impact of modeling binary black hole populations using analytical fits to cosmological simulation star formation histories. And so, gravitational waves from the mergers of stellar mass double compact objects can be used to probe massive star formation and evolution throughout cosmic history. And next generation detectors are going to be able to detect mergers out to redshifts as high as 20. But even current gravitational wave detectors may be detecting mergers from binaries that originated at high redshifts due to the delay time between the formation of the progenitor binary and its eventual merger as a double compact object merger. And this delay time can be anywhere from several million years to many billions of years. And so this delay time and the formation efficiency of merging double compact objects, and particularly binary black holes, is very strongly dependent on the metallicity. And so their mergers can be additionally used to probe the chemical enrichment throughout cosmic history. And so to make the most out of our current and future gravitational wave observations, it is critical to very carefully model populations of gravitational wave sources, and particularly binary black holes, if we're especially interested in metallicity evolution. And so to model a gravitational wave source population, there are two key components that you need, as was very nicely introduced in the previous talk. So you're going to need some kind of binary evolution model, for which we use the population synthesis code COMPASS. And you also need a star formation history, or a metallicity-dependent star formation rate density, which is going to tell you about the number and metallicity of stars that formed at different times throughout cosmic history. And that is the piece that I'm going to focus on in this talk. So the SFRD is a difficult quantity to observe and model. And so one way that you can go about modeling it, and has been used fairly commonly, especially in population synthesis calculations, is to use analytical models that represent the SFRD. These are generally fairly convenient from a computational standpoint, because it is fairly easy to vary the physically motivated parameters and therefore quantify uncertainties in them. And the analytical model that we are going to use in this work is a combination of the Maddow-Dickinson form of the just redshift-dependent star formation rate density without metallicity evolution in it, and convolved with a metallicity distribution function. We're going to use a skewed log-normal metallicity distribution because that is a fairly commonly used form. That is also the default in COMPASS. And so these are fairly widely used, they're convenient, but the question is, how well do these analytical models actually represent the full underlying SFRD? Because this is a difficult quantity to observe due to limitations on observations, particularly at high redshifts and low luminosities, and it is therefore fairly difficult to constrain and model. And so the way that I am going to go about answering the question of whether analytical fits can represent a more detailed SFRD is by using the cosmological simulation of galaxy and formation and evolution, illustrious TNG. So these simulations, there are 3 different boxes that I am using. They have all of the same physical assumptions and initial conditions, but they have different resolution and volume, where TNG 50 has the highest mass resolution and the smallest volume, and 300 has the lowest resolution and the largest box size. It includes several galaxy clusters in it. And what we are going to do is construct the true SFRD of the simulation, because that is something you can do with a cosmological simulation, because for every star-forming gas particle in the simulation, you can just read off its metallicity and its star formation rate at all of the different redshift snapshots of the simulation. So we can construct an SFRD, and then we can fit an analytical SFRD model to it and see how those compare. So let's take a look at what one of those would look like. So this is for TNG 100. It is the intermediate box size and volumes. That's why that's the one I'm showing. And here in color, I show the SFRD of TNG 100. And in the black contours, I have the analytical fit to it. The panels, the top panel is averaged over metallicity. The side panel is averaged over redshift. And so here, just even qualitatively, we can see that in the high metallicity regions of the plot and in the low metallicity and high redshift, the contours, the fit is not doing a very good job to fit to the model. And if we look at this metallicity distribution on the side, we can see that especially at high metallicities, that is partially caused because the fit is smoothing over the secondary peak in the simulation SFRD. And so if we just take a look at what a metallicity average SFRD would look like for the different simulations, just to get a sense of how the three compare to each other, the main difference really is just the normalization that goes up with simulation resolution, and the peak shifts toward higher redshifts. These are just resolution effects. I'm not going to focus too much on that, but keep that in mind for future plots. And so now we have a simulation SFRD and an analytical fit to it. If we combine this with our COMPASS binary population synthesis model, we can now look at our binary black hole merger population. Let's take a look. So this is just the merger rate density and over redshift. And so here we can see that at the high redshifts, the difference between the fit and the simulation is amplified even more, and the fit is overproducing binary black holes, or the rate of binary black holes at higher redshifts, while at low redshifts, it doesn't look quite nearly as bad, right? But then, if we take a look at the mass distribution at redshift 0.2, where based on the rates it looked fairly okay, we can see that the analytical fit in the dashed lines is overproducing binaries at about 8 solar masses, and on the other end of the mass spectrum, it is underproducing binaries in all of the upper masses. And so this is fairly concerning, right? If we're going to take those analytical models and be representing a more detailed SFRD with them, this could possibly be biasing our mass distributions. And so let's take a look at where those binaries might be coming from. And so now I split up that redshift 0.2 mass distribution into redshift and metallicity bins, where redshift is the color and metallicity is the line style. So there's a lot of lines. I'm just going to draw your attention to the solid lines. And because those are coming from that high metallicity bin. And as you can see, if we focus on the bright green line, you can see that it goes up between the simulation and the fit. It goes up by about an order of magnitude, right? And all of those solid lines are kind of between 0 and 20 primary mass. And so we can see that that peak that the analytical fit is overestimating is coming from this high metallicity bin. And if we look back at what that would look like here, and specifically, let's highlight that high metallicity bin in this from the other plot. So those binaries are coming from this region where the analytical fit is overestimating the SFRD, because it is trying to smooth over this secondary peak feature in the mass distribution, or in the metallicity distribution of the true TNG SFRD. And so this is mostly to say that you need to be careful when using analytical fits to more complicated, more detailed underlying star formation histories, and that this is something that could be affecting the populations that we are modeling. And so, kind of to raise some questions of where do we go from here, there's, of course, as we heard from the previous talk, other ways of modeling SFRDs. So I would love to hear thoughts about where to kind of go next, whether analytical fits are even worth trying to improve, or it might be better to stick to more detailed ways of modeling SFRDs for these purposes. Great, thank you.
Thank you. Very interesting talk. I wish you had more time. One of the things, since you're using Compass's default supernova algorithm is wrong. So that doesn't mean we know what's right. But you might want to look at a variety of other algorithms for the mapping to neutron stars, black holes, etc.
Yes.
And we should talk offline. But the one that is the default in Compass is wrong.
Okay. I am not entirely sure if we're using the default one. I'm using the population from Lika's paper in 2022. So I'm not entirely sure if it is the default one, but yeah, we can talk.
It's a fair question, Selma de Mink. But stay closer to what you're investigating, this analytic fit. I'm saying something obvious here, but of course the TNG simulations are not the final word. And so there's a few things that are well known. We did a paper with Rudiger Pakmore. It doesn't have such nice plots as you, but I think it has some of the messages. So I think it's very hard to resolve the low metallicity halos, and so it's under-representing that. And so it would be good that even if you have a nice fit, that we leave more room in the models there.
Yes,
I'm blinking.
that is something.
Oh yeah, the second thing, as we may be able to see in your plots, is it's producing, I think, way too high metallicity at redshift 0. Can we see this in the plot? Yeah, so show the nice plots, your length, Z versus Z.
It went way too far.
Yeah.
This one?
So the y-axis is Z over Z solar, and it's going up to 10 times solar. Well, yes. we don't have stars with 20% metallicity, but TNG has, right? So, so I think that's the main things to worry about here that I wanted to point out. But
those are all things I've been thinking about, like investigating kind of the next steps.
But nice study, and I think analytic fits have a lot of use because they're fast and flexible.
Yes.
Hi, Mike Zevin. Can you go to the mass distribution plot that you had? Or this too, actually. Yeah, sorry, the R of Z is fine. But yeah, my question is, this one's a little complicated, but if you go to the one that you were showing previously, so when you're using different box sizes for the TNG simulations, you are seeing a pretty significant overall normalization to the merger rate. So what's being captured in these higher box sizes in the large-scale structure that's leading to the decrease in the merger rate when you go up to the 300 megaparsec?
In general, that is mostly a resolution effect. And basically, it is coming from the fact that in TNG 300, which has the lowest resolution, it basically treats it as like a particle, while a particle is like not massive enough, it treats it as if it almost like doesn't exist. And so like you're forming stars and gas particles kind of later in the simulation because the particles need to get massive enough before it's going to treat it as if it like exists, because it needs to have higher enough mass to be like recognized with the mass resolution. And so because of that, like TNG 300 is going to start forming stars later, and so because of that, it's overall going to end up having a lower like star formation rate, and then this ends up affecting the amount of black holes that we're getting.
Yeah, maybe we'll take one more question from Martina, and then maybe while the next speaker could come set up.
Yes, thank you. This is to follow up on Mike's question, or actually give maybe a different response. So I think the main resolution effect here is that when you increase the resolution, you can have smaller galaxies, and you can also have higher star formation rates. Resolution typically allows cosmological simulations to reach higher star formation rates, so you have higher overall cosmic star formation rate density, and you also have more low metallicity star formation, both of which boosts the rate. And yeah, as a suggestion of what's a possibility where to go next? I shamelessly mentioned my work where we just do observation-based models for the metallicity-dependent cosmic star formation history. So that's another possibility, also allowing you to probe uncertainties.
That's something I've been thinking about for future work. Thank you.
Perfect.